We are on the discussion of chemical equilibria. In fact, in the previous lesson, we concluded most of it, and we did the mixed calculations of the K, C, and Kp, and I think they are out. And to continue with the last bit of the tute and to conclude with the revision, this is about the acids and bases. Study on the acids and bases. In fact, the definition of acid in the early 19th century, where at that point as no litmus was discovered. So testing or the test for the acid is simply was tasting it. Test for the acid in the early 19th century was simply tasting it, right? That means anything which has a sour taste, they classified anything which has a sour taste as acid. And afterwards, once the litmus was discovered, so they said that any substance which turned litmus red, litmus solution or the litmus paper red, or defined as acids. And later on, Arrhenius came forward and gave a better understanding or definition of an acid. Arrhenius said any substance which produces excess of H+ ions in aqueous media. Any substance which produces excess of H+ ions in aqueous media are acids. And then the that particular definition was further extended by Bronston and Lowry to include non-aqueous solvents. So this is 3 stages, right? In the definition of acids, I would say first is the tasting, and then the litmus test. And Arrhenius said anything which gives H+, that's the 3rd stage. And we are in the final stage of the definition, which is the most accepted definition of acids and alkalis, which is the Bronston-Lowry theory of the acid. So Bronston-Lowry theory includes the non-aqueous solvents as well, because Arrhenius said any substance which gives H+ ions in aqueous media he defined as acids, but this definition was further extended by the Bronston and Lowry to include the non-aqueous solvents. Now, as to the Bronston-Lowry theory of acids, acids are defined as any substance which donates protons. Anything which donates protons, in what is referred to here as protons, is H+, because H+ ions is just simply a proton, right? It's simply a proton is H+, and any substance which accepts H+ ions is a base. Any substance which donates H+ ions was defined as acid, and any substance which accepts H+ ions were defined as the bases. So H+ ions here is protons, because hydrogen has a single electron. When this hydrogen's one and only electron is lost, the left behind part is H+, which is the proton. So that's why we call the H+ ion as the proton, right? It as only proton. So any substance which gives H+ ions were defined as the acid, and any substance which accepts H+ ions were defined as the base. Now, as for the acid-base behavior of the substances, when an acid donates a proton, for example, say I'll take ethanoic acid. Why we call ethanoic acid as acid? Because in aqueous media, it donates protons and forms the ethanoate ion and H+ ions. This ethanoate ion and the H+ ions is ethanoate ion and the H+ ions. Ethanoate ion is especially unstable. So it accepts H+ ions and forms the acid again, right? So now you can notice when acid loses a proton, the left behind part is a base. the left behind part is a base, because this base it can accept H plus and forms the acid again, right? So when an acid gives out a proton, the left behind part, which is this part, is a base, and when the base accepts a proton, the left behind part will be an acid. So now look at this. This is something new. Acid reacting with base. Right? Now we know up to this point acid plus base is salt and water. But as for the Bronston-Lowry theory, that's not the case. I'll answer your question why giving hydroxide ions are not bases in a while. So acid, as I mentioned before, will donate protons, give protons to the base, right? Because base is the proton acceptor, right? So I'm going to write this as acid 1 and base 1, right? Or the base 2. This acid will give a proton to the base, because acids are proton donors. You notice here that acid proton donors, it gives protons to the base. And when acid gives the protons to the base, it forms the base 1. And when, meaning the new base, it forms a new base. And when the base accepts a proton, it forms a new acid. See? When acid gives the proton, the left behind part is the base. So when acid donates the proton, the left behind part is a new base. So when this acid gives a proton, it forms a new base. So this new base is formed from this acid. And when the base accepts a proton, it forms the new acid. Right? Clear? So acid-base reaction can be written in this way. Acid reacting with base gives new base and a new acid. This, the previous equation, the ethanoic acid is acting as an acid, as to the Bronston-Lowry theory. Because as to the Bronston-Lowry theory, any substance which donates H plus ions are referred to as acids. So ethanoic acid is acting as an acid here because it gives H plus ions. Right? See, you can see ethanoic acid. As it gives H plus ions, it forms ethanoate ion. But because it gives H plus ions, it is an acid. But after giving the H plus ions, what has happened to that acid? It has become a base. Why? Because this acid, being a weak acid, it can combine with this H plus and form the unionized acid again. Right? So here in the equation, H plus is not the acid. Ethanoic is the acid. Ethanoic acid has given the H plus ion. Any substance which gives H plus ions is what is defined as an acid. When an acid gives H plus ions, it forms a new base. And the base will take H plus ions from the acid, because as to the Bronston-Lowry theory, base is a proton acceptor, and it will take H plus from the acid and forms a new acid. Right? See the base, imagine this is the base, combines with these H plus ions and forms a new acid. So acid-base reaction can be represented as this way. We don't define the base as hydroxide ion giver. The one which gives hydroxide ions is not a base, it's an alkali. The one which gives hydroxide ions is not a, we can call it an alkali. That is much better word, because not, for example, sodium hydroxide, right? It's alkali. It gives OH minus ions, right? I hope you know the difference between the base and alkali. This is done in grade 9, right? Bases are what? Metal oxides. Metal oxides are bases, and metal hydroxides are alkalis. Some bases are not alkalis. because some bases, for example, if you take copper oxide is a base, metal oxides are bases. But the copper oxide will not dissolve in water to form an alkali. You don't react copper oxide with water and from copper hydroxide. Likewise, aluminium oxide is a base metal. All metal oxides are bases. But not all bases are alkalis. Why? Because, for example, aluminium oxide is a base, right? It's a base because it's a metal oxide, but it doesn't dissolve in water. It's not an alkali. So not all bases dissolve in water to form hydroxide. So not all bases are alkalis, but all alkalis are bases, right? All alkalis are formed when a metal oxide dissolves in water. So hydroxide, we call it as a alkali, and because of that, you cannot call all bases as alkalis, but you can call all alkali as a base. That can be done, right? So giving hydroxide is a base, yes, that is a base, but alkali, that's much better word. But all alkalis are bases. All alkalis are base, but we don't define alkali as a or base as a substance which gives OH minus signs. No need to be a OH minus donor to become a base. If any substance which takes H plus, it's also a base. For example, can you see ethanoate ion? Right? It's a base, but it doesn't give hydroxide. It takes H plus ions. So as to the Bronston-Lowry theory of acids and bases, base is a substance which don't prove accepts H plus ions, not a substance which gives OH minus ions. I hope it's clear. Right? You can copy this for the question 3. Acid plus base gives new base and new acid. So when an acid donates a proton, the left behind part is a base. For example, ethanoic acid. After giving the H plus, it forms ethanoate ion. Ethanoate ion. CH3COO minus. Likewise, a base. Ammonia is a base. It takes H plus ions and form ammonium ions. So these pairs, when acid donates a proton, it left behind part is a base. When base accepts a proton, the left behind part is the acid. These pairs, which differs by a single proton, is referred to as acid-base conjugate pairs. Conjugate pairs. Conjugate pair difference will be always one single H plus. This is a conjugate pair. This is also a conjugate pair. What's a conjugate pair? A pair, acid-base pair, which differs by a single proton. So when acid donates one proton, the left behind part is a base. That base and this acid together is a conjugate pair. In this example, ethanoic acid and ethanoate is a conjugate pair, right? And ammonia, it can take H plus ions because ammonia, the nitrogen has a lone pair. It can easily form a dative bond with H plus. So ammonia, after it forms a dative bond with H plus, it forms the ammonium ion. So ammonia is base. After accepting H plus is formed the acid, new acid. So the acid-base pair, which differs by a single proton, one single proton, is referred to as the acid-base conjugate pair. For example, if you take sulfuric acid, it's acid because it gives H plus ions. And when it gives say it gives two H plus ions and forms sulfate. Now, can you tell me what is the conjugate, if is there a conjugate pair here? If that's the case, what is the conjugate pair? Okay, before this question, I will take another example. I'll come to that example in a while. This one, H plus and hydrogen sulfate. Can you name the conjugate pair here? Let me complete the explanation. After that, I'll attend to all your questions. The sulfuric and the hydrogen sulfate, right? That's a conjugate pair. Now, if I were to write this expression, what is the conjugate pair here? Yes, what's the conjugate pair here? No. There's no conjugate pair here. Now see the earlier one, the conjugate pair is sulfuric and hydrogen sulfate. H plus is not an acid. Who said H plus is an acid? In equation, H plus is never an acid. When an acid donates a proton, that is H plus. That is the acid. Sulfuric is the acid. H plus is not an acid. Of course, when there are aqueous H plus ions in the medium, we call it as acidic. H plus itself is not called as an acid. Anything which can give H plus ions is an acid, right? For example, if I can give H plus to you, I am an acid. What I am giving, H plus, is not an acid. I am the acid because I am giving the H plus. The substance which donates H plus is an acid. H plus itself is not an acid. H plus itself is not an acid. The substance which gives the H plus is the acid, right? Because H plus is just a proton. If you call H plus an acid, this should be able to give H plus. Can H plus give H plus? No, you can't, right? So any substance which gives a proton is an acid. Can a proton give another proton? You cannot. So when an acid donates a proton, the left behind part is the base. This is the base, hydrogen sulfate. So sulfuric and hydrogen sulfate is a conjugate pair. Not sulfuric and H plus is a conjugate pair. So conjugate pair always differs by a single proton, right? And likewise, you have this sulfuric and sulfate. It is not a conjugate pair because the difference is not a single proton. It says two protons. Conjugate acid-base pairs differs by only a single proton. Okay, let me check the equations. I'm going to explain. Don't worry, again and again and again. No problem. I know it's a new concept. Is H plus in the previous equation is an acid? You know the answer. It is not. Anything which gives H plus is an acid. That is answered. According to the different theory, definition of base changes. According to different theory, the definition of base changes. Base is defined as any substance which accepts protons, as to the Bronston-Lowry theory. Right? I said metal oxides are bases. That is how you identify a base. But anything which can take H plus is the base. That's the Bronston-Lowry theory of the bases. There's another question. Can we call H plus ion as an acid? No. H plus ion is not an acid, but if you get H plus ion in the solution, that solution is acidic. But anything which can give H plus is the acid. And the answers, sulfuric and H plus, they are never conjugate. Conjugate means when acid gives H plus, the left behind part is not H plus, right? When sulfuric gives the H plus, the left behind part is hydrogen sulfate. These two are the conjugate pairs.